I'm Ning Chen from Shandong University. I am honored to present our work EXGAZE. This research was conducted in collaboration with my colleagues at Shandong University and the University of Warwick. Gaze or eye tracking has emerged as a crucial HCI technique in XR, and it is rapidly being adopted in many head-mounted displays. The human eye can move at a high speed, reaching up to 700 degrees per second. However, the frame rate of common frame-based cameras usually operates at 30 to 50 Hz, which is unable to capture the details of faster movements. This makes it difficult for frame-based methods to meet the requirements of applications that demand high tracking frequency. Also, likely iLink 1000 Plus can achieve a tracking frequency of 2 kHz. They use high-speed cameras and require high computational resources, thus having limitation in practical applications. Even cameras characterized by their high temporal resolution are emerging as a viable solution. Even cameras detect pixel-wise intensity changes independently, generating a synchronous and sparse event stream instead of synchronous video frames. They have high temporal resolution and low resource consumption, can capture events at microsecond intervals. However, existing event-based methods struggle to achieve a balance between accuracy and efficiency. Some methods, such as Swift-Eye, offer high accuracy but come with high computational costs. Others, like 3T, have lower computational requirements but suffer from relative low accuracy. Therefore, we propose ESGAZE, a gaze tracking system designed for on-device extended reality, which strikes a balance between accuracy and efficiency. ESGAZE tracks the position of the pupil to determine the point of gaze, and it can be divided into 4 modules. The frame-based initialization and relocalization module can robustly localize the pupil, but it operates at a low speed. The event-based pupil tracking, on the other hand, can offer a high tracking speed, but there is a potential for target loss. To combine these 2 modules and take advantage of their strengths to achieve a balance between accuracy and efficiency, we have introduced a lightweight and efficient approach adaptation module. Most of the time, the event-based module is employed for tracking, and the approach adaptation module is used to assess the tracking result. If the deviation exceeds a certain threshold, the frame-based module will be triggered for relocalization. Finally, the gaze regression module uses polynomial regression to map the pupil position to the point of gaze. In detail, the frame-based initialization and relocalization module uses the MobileNet V3 small as the backbone and combines with 2 detection heads for eye region and pupil detection respectively. We represent the eye region with a rectangle, and following Swift-Eye parameterize the pupil as an ellipse. Eye region detection is only carried out at the beginning of the whole system. By detecting the eye region, we can crop the subsequent image, thereby reducing the data size to be processed. The pupil detection provides an initial or corrected pupil location for subsequent event-based tracking. Before introducing the event-based pupil tracking module, I would like to clarify 3 facts. First, the motion information of the pupil can be obtained from the event generated around the pupil. Second, the sparsity of events can be utilized to accelerate computations. Finally, for existing GPU acceleration technologies, regular and consistent computations are more easily accelerated. For example, although sparse convolution theoretically has fewer computations than regular convolution on sparse data, due to the need for additional calculation to maintain the sparse data, it cannot be well accelerated on GPUs. As a result, it may require a longer computing time compared to regular convolution. Based on these preliminaries, we proposed the sparse event patch representation. It takes advantage of sparsity and is conductive to GPU acceleration. Specifically, first, we sample endpoints on the pupil ellipse obtained from the latest tracking at a radian interval of 2 pi over m. Centered on these points, square patches of the same size are cropped from the event frame. These sparse event patches can then represent the movement of the pupil. We've proposed the sparse event patches transformer to extract eye movement information from the sparse event patches. It consists of a patch-shared convolution neural network and a transformer encoder. The patch-shared CNN is used to extract the local features from each event patch simultaneously, and learnable positional embeddings are added to maintain the positions information. Then, a transformer encoder fuses the features, and average pooling is performed on the fused features to obtain a global feature vector. This global feature is then fed into a fully connected layer to calculate the offset of the pupil region. As mentioned before, we introduced the approach adaptation module to take advantage of both the frame-based and event-based modules. When frame data is obtained, instead of immediately invoking the frame-based module to localize the pupil, we use the gradient-based template matching method to calculate the similarity between the latest tracking result and the corresponding position in the frame. If the similarity is higher than a certain threshold, we consider that the tracking result is matched and continue to use the event-based module for tracking. However, if the similarity is low, it indicates a deviation, and we will call the frame-based module to correct it. In the experiments, we utilized two datasets, UAI and OpenEDS 2020. The UAI dataset contains both event and frame data, which we use for model training and parameter selection to verify our algorithm in VR environment. We employ the OpenEDS dataset. Given that it only contains the frame data, we use V2E to generate the corresponding event data. We compare EXGAZE with four state-of-art event-based eye tracking methods: UAI, SwiftEye, 3ET, and Retina. The demo video below illustrates their tracking accuracy on the UAI dataset. EXGAZE and SwiftEye consistently deliver accurate tracking, even during blinks, while UAI cannot track during blinks. 3ET and Retina provide results only when there are clear pupil movement. The following showcase compares tracking accuracy with computation time on the two datasets. EXGAZE was the most efficient on the EVI dataset in both aspects across various movement types. While SwiftEye offers higher accuracy, it is computationally expensive. On the other hand, 3T is efficient but has a higher pixel error. EXGAZE, however, achieves both high accuracy and low latency. On the OpenEDS datasets, without fine-tuning, it also achieved comparable accuracy to more complex methods. The results demonstrate that EXGAZE outperforms other event-based eye tracking methods by striking the best trade-off between accuracy and efficiency. At last, to verify the real-time performance of our method, we evaluated the runtime of each module on a JSON Orinono with results summarized in Table 1. The event-based module has an average runtime of 0.32 milliseconds, well within the 0.5 milliseconds for 2 kHz tracking. The frame-based relocalization module with an average runtime of 1.17 milliseconds is used only when needed. The overall average runtime per tracking operation is 0.407 milliseconds, meeting real-time requirements. In conclusion, we introduce EXGATE, an event-based real-time and high-frequency eye tracking system. To leverage the sparsity of the event string, we propose a sparse event patch transformer to achieve efficient eye tracking. Additionally, we design a lightweight event frame approach adaptation scheme to guide the system switch between frame-based and event-based approaches. Through our evaluation and comparison with SOTA methods, EXGATE demonstrates the best trade-off between tracking accuracy and efficiency.